Hey everyone, welcome back to Education is Life, your go-to channel for unlocking the wonders of learning. It is me, Joe Edgo, and today we're diving into Lesson 8 of the Arduino Uno R4 Minima Ultimate Training Series, focusing on RGB LEDs and Pulse Width Modulation. In this lesson, you'll learn how to control RGB full-color LEDs through PWM using the analog write function. You'll learn how to produce a variety of colors by mixing the red, green, and blue primary colors. You'll also learn how to produce a glowing effect and fading effect on RGB LEDs. And finally, you'll learn how to create an automatic RGB LED project that gradually changes its color from shades of red to shades of green and shades of blue continuously. So, if you want to learn how to build this project step by step from scratch, then watch this lesson till the end. As always, before we start, I'd like to extend my sincere gratitude to SunFounder for sponsoring this course and enabling everyone, especially beginners, to embark on this comprehensive educational adventure. SunFounder has kindly donated this Arduino Uno R4 Minima Ultimate Sensor Kit, which will be our constant companion throughout this series. So, if you're still searching for resources to help you in your journey with the new Arduino Uno R4, I recommend you give this one a look. This is available on the SunFounder website as well as on Amazon. The links are in the description below. So now, let's begin. For this session, you need the following materials: a common cathode RGB LED and 3 pieces 1 kilo ohm current limiting resistor. Or if you already have your SunFounder kit, you can simply use the RGB full color LED module. Please note that this module already includes 3 current limiting resistors of 150 ohms each, so it is your decision if you are going to add more resistors in series to suit your needs, considering that Arduino Uno R4 has a maximum current draw of 8 mA per GPIO. Of course, a breadboard, some connecting wires, and your Arduino Uno R4 Minima. In our previous lessons, you learned how to read analog signals and how to use them in Arduino digitally. We also covered how to use the digital pins of the Arduino to control digital devices like turning on and off LEDs. In this lesson, we'll explore how Arduino Uno can be used to send analog signals to control devices like changing the brightness of LEDs instead of simply turning them on or off, generating musical tones, driving motors at various speeds, and a lot more. The Arduino Uno R4 has two ways to send analog signals to control analog devices, either through the digital to analog converter pin at pin A0 or through pulse width modulation at pins 3, 5, 6, 9, 10, and 11. Our focus of today's discussion is pulse width modulation. Pulse width modulation, or PWM, is a technique for getting analog results through digital means. Just to make it clear, PWM does not produce true analog results, but rather it simulates or mimics analog output voltages using digital control. So, how is it done? Digital control is used to create a square wave, a signal that is switched between on and off. Now, this on and off pattern can be used to simulate voltages between the full VCC, 5 volts, and 0 volts by changing the portion of the time the signal spends on versus the time that the signal spends off. The duration of this on time is called pulse width. So, to get varying analog values, you change or modulate that pulse width. And if you repeat this on and off pattern fast enough, the result is as if the signal is a steady voltage that is between 0 and 5 volts. The Arduino Uno R4 has a PWM frequency of 490 Hz for all its PWM pins. This is similar to the previous version except for pins 5 and 6. Arduino Uno R3 has a frequency of 980 Hz on these pins. So, what does it mean? The term frequency is synonymous with clock speed, clock rate, or the number of clock cycles per second. And a time period is a duration that is the inverse of the frequency. So, if we get 1 divided by 490 Hz, it gives us 0.002 seconds or 2 millisecond time period. meaning a 2 millisecond time period for each clock cycle in an oscillating clock signal. Thus, we can say 490 clock cycles per second, or simply 490 Hz. In Arduino, we can use the analog write function to generate a PWM signal through its PWM pins. By default, the analog write resolution is set to 8 bits, which means that we have a range of decimal values from 0 to 255 to represent analog values from 0 to VCC, which is 5 volts in this case. So, a call to analog write function is on a scale of 0 to 255. For example, analog write 255 requests a 100% duty cycle, which is always on, simulating an analog output voltage of 5 volts. The analog write 127 gives us a 50% duty cycle, which is on half of the time. This is like saying half of 5 volts, which is 2.5 volts. The analog write 64 gives us a 25% duty cycle, or 1/4 of 5 volts, which is about 1.25 volts. And the analog write 0 gives us a 0% duty cycle. This is the same as producing an analog output of 0 volts. To demonstrate this concept, let's hook up this simple circuit diagram where we have 3 individual LEDs, red, green, and blue. However, instead of using individual LEDs, I'll use a single RGB LED. An RGB LED is basically an LED package that has 3 internal LEDs, red, green, and blue, that are very close to each other. This LED design is based on the RGB color model, an additive method of color mixing in which the red, green, and blue primary colors of light are added together in various ways to reproduce a broad array of colors. For example, mixing blue light and green light gives cyan light. Mixing red light and green light gives yellow light, and so on. It has many applications, particularly in displays of electronic systems such as televisions and computers. RGB LEDs can be either a common anode or a common cathode type. In a common anode RGB LED, the positive terminals of all the internal LEDs are all connected to the external anode pin. Thus, you need to connect the anode pin to the positive terminal of the power supply, and to control each color, you need to apply a low signal to the red, green, and blue pins. In a common cathode RGB LED, the negative terminals of the LEDs are all connected to the external cathode pin. This cathode pin then needs to be connected to the ground of the power supply, and to control each color, you need to apply a high signal or logic 1 to the red, green, and blue pins. Thus, when you look at an RGB LED, you'll see that it has 4 pins. The longest pin is the common anode or the common cathode pin. It has a pin out of red, anode or cathode, green, and blue pins. So I'll connect the red pin of the RGB LED to the Arduino PWM pin D11, the green pin to D10, and the blue pin to D9. Now, what I have here is a common cathode RGB LED, so I'll connect this common pin to the ground. In our sketch, I'll define the red pin, green pin, and blue pin. When using these pins as PWM pins, you are not required to configure them as output. So, I'll just set up the serial communication, and then, in the loop function, if I want to turn on the red LED, let's say at 100% duty cycle, I could simply call the analog write function and pass in the red pin with a value of 255. This simulates 5 volts. Then, let's have a simple delay of 1 second, and then I'll change the color to green. And to do that, I'll turn off first the red LED, so analog write, red pin 0. This is 0% duty cycle, which simulates 0 volts. And then, analog write, green pin 255 to turn on the green LED. I'll add another 1 second delay before turning on the blue LED. So, I'll turn off the green pin first before turning on the blue pin. And finally, I'll add another 1-second delay to turn off the blue pin before looping and repeat the entire process. I'll upload the code and see how it looks. And as you can see, it works. We can see the red, green, and blue primary colors turning on and off one at a time. Perhaps you realize that we can also accomplish this program by simply using the digital write function instead of using the analog write. And that is correct. However, when using the digital write function, we can only turn on and off each color, but we cannot adjust the brightness levels of each color to produce any color that we want. To adjust the brightness, we can use any value from 0 to 255. Please note that this is the range because we are using the default 8-bit resolution. We can change this up to 12 bits by calling the analog write resolution. For now, let's stick to the default resolution. So, I'll change this to a dimmer red, say 64, then a dimmer green, say 32, and a much dimmer blue, say 16. I'll upload the code and see how it looks. And it works. We see a much dimmer red, green, and blue lights. However, you've noticed that the green LED is still a bit brighter even if I reduce the duty cycle to only 32. That is 1/8 or 12.5% duty cycle. If you have access to the datasheet of the RGB LED that you're using, you can check the forward voltages of the internal LEDs. Then, you can calculate the write resistance of the resistors that you're going to use so that you can balance the brightness of the internal LEDs. Because here, I'm using the same value of 1 kilo ohm resistor for the 3 colors. If you have your SunFounder kit, you can also use the RGB Full Color LED module. This module also uses a common cathode RGB LED. However, the pinout is arranged as common ground, red, green, and blue from right to left for easy connection. So, I'll replace this and it works the same way. To create a program for an LED glowing and dimming effect, we can apply our previous knowledge in looping statements. Let me comment out this code first. Now, we know that we send an analog-like signal to the PWM pins from 0 to 5 volts using the digital values from 0 to 255. So, instead of placing here some fixed values like 64, 32, 16, or 0, I'll create a loop that increases the value from 0 to 255. So for int value is equal to 0, value is less than to 256, and then value plus plus. And then inside the loop, I'll call the analog write function and use this value variable. This should gradually increase the brightness of the red LED. However, this loop is going to execute so fast that you might not see the change from 0 to 255. So, I'll put a short delay of 15 milliseconds for every loop. And then, after the red LED reaches a maximum brightness, let's gradually fade it. So, to have a dimming effect, I'll duplicate this code and change the starting value from 255 down to 0. It means that I need to change this condition so long as the value is still greater than or equal to 0, and then I'll perform the code inside and then decrease the value variable by 1. Now, this is just for the red LED. If we want the same thing to happen for the green and the blue LEDs, we need to duplicate these two looping statements twice. So, I'll change this to green pin, and then this to blue pin. Now let's upload the code and see what happens. And as you can see, we have a nice glowing and fading effect of the red, green, and blue colors. Although we've seen the effect of using PWM to control the LED's brightness levels, we haven't seen this RGB LED producing a mixture of different colors. If you open any application on your computer that allows you to choose a color, like a font color in MS Word, Photoshop, or Paint, you'll see that you'll be able to produce any color that you want by having a mixture of red, green, and blue lights. Say, to produce a shade of purple light, I could use 142, 51, and 163 for the red, green, and blue colors respectively. To produce a shade of teal color, I could use 60, 163, and 156. And to produce, let's say, a shade of gold, I could use 163, 147, and 41. Let me comment out this code first, and then I'll uncomment this previous code and replace these RGB values with 142, 51, and 163 to produce purple. Show it for 2 seconds and then change the color to teal. So I'll duplicate this code and replace the values with 60, 163, and 156. And finally, I'll duplicate this code one more time to produce a gold color that is 163, 174, and 41. Now, I'll upload the code and see how it looks. And we were able to produce the expected color by mixing the right amount of red, green, and blue lights using pulse width modulation. For your challenge activity, I want you to improve this program to make an automatic changing color RGB LED project. As a hint, you can get an idea from any color picker application of how you would gradually change the value of each color so that it produces a smooth transition between various shades of colors. Notice here that as the red is gradually mixed with the green light, it produces a touch of orange up to yellow light. And as the red light is gradually reduced, the green light is intensified, producing a more solid green color. And as we continue adding the blue light, it produces teal up to cyan. And as the green light is reduced, the shade of blue is more intensified. Now, adding red to the blue produces shades of purple. And as the blue light is reduced, it turns to pink and eventually turns red, and the cycle repeats. Again, thank you so much for joining me in this lesson on controlling RGB LEDs through pulse width modulation. For our next lesson, we'll work on the same RGB LED project. However, I'll introduce you to another important constructs in Arduino C programming, creating custom functions, and the use of array in managing and organizing your data. These are very important topics in the world of programming, as this would allow you to create more efficient codes that are reusable, flexible, and easy to maintain. If you found this lesson enlightening, don't forget to hit the like button, Subscribe for more knowledge pack sessions and ring the bell to stay updated. So, keep learning, keep experimenting, and keep in mind, education is life. See you in our next lesson. Happy coding!